All right, before we do the mathematics of a reversible adiabatic compression or expansion of an ideal gas, let's draw a picture of what a process like this would look like. So we have to envision some sort of cylinder, and the cylinder is insulated. So there's no heat transfer, right? Because we just said this was an adiabatic process. And so we might draw in some sort of styrofoam or some other kind of insulation on this cylinder. You can imagine the cylinder has a piston that can be pushed in, and that would make it an adiabatic compression. And we can imagine doing that with we've got some gas molecules in here. Great. Well, when we do this process, we actually don't even have to have the insulation if we work really fast. If we imagine just jamming this piston in, that would be an adiabatic compression, at least approximately, because heat transfer takes time. So if we compress something rapidly, it will be an adiabatic process. Of course, if we do it rapidly, then it will not be reversible. Okay, so there's the process. So the goal here is to come up with a relationship between the pressure in the cylinder and the temperature in the cylinder and the volume of the cylinder. So somehow to relate those three variables. Okay, and the way we can approach this is to look at the fundamental definitions of internal energy and how internal energy is going to change during this process. So we'll start off with our most fundamental total differential for change in internal energy. du is equal to cv dt plus pi t dv. And we look and say, is there anything we can say about this statement based on the fact that our process is reversible and that it's adiabatic and that it's happening with an ideal gas? Okay? Well, you say, aha, it's an ideal gas. Pi t is equal to 0. Okay, we might even want to annotate our notes here with why we could say that pi t was equal to 0, so that we don't misapply something. Great. All right, what else can we say? Well, we could write the first law of thermodynamics, that the change in internal energy is equal to the work and the heat flow. So we'll write those out as infinitesimal changes. And then say, all right, is there anything we can say about this equation? Well, yes, we can cross off this term because we know that the process was adiabatic. So we can just make a little notation here, adiabatic. Great. So now we have two expressions for the change in internal energy, and we can equate them. We can say that the heat capacity times dt is equal to the work. And work, say, is equal to negative P external dV. Well, at this point, we've got an expression with T, we've got an expression with V, but we don't have the pressure in the system. We have the external pressure. But we know that it's reversible. So if it's reversible, we can replace the pressure in the system with the external pressure. So we can equate those two. So we can say that the work is negative P times dV. And we make that substitution because it's reversible. So notice that all three phrases that we started off with played into the equation that we ended up with. Okay? All right. So now what we can do is say, all right, I've got pressure, volume, and temperature. I've got three variables. I can't do an integral unless I have just one variable on each side. So let's go ahead and make one more substitution, and that's that we could substitute pressure with nRT over V. And we can say that we can do this because it's an ideal gas. Okay, so now you say, okay, I've got two variables on this side, so I'll divide both sides by T. So I'll get CV times dt over T. And on the right-hand side, I'm just going to have negative nR times dV over V. And just to save time, we can divide both sides by the number of moles. So we'll get the molar heat capacity times dT over T is equal to negative R times dV over V. Okay, so we're just about ready to integrate. Let's go ahead and do that on the next page. So we've got CV per mole dT over T, and we can integrate that from some initial temperature T1 to some final temperature T2, and we can do the same thing with the other term, which was negative R times dV over V. So we can integrate from some volume to some other volume. Great. And if we assume that the constant volume heat capacity is constant, we can go ahead and pull that outside the integral. And then we just get the integral of dt over t, and that's a logarithm. So we have the log of t2 minus the log of t1. Or we can just say it's a logarithm of the ratio of the temperatures. And then we end up with the same thing on this side, negative r times the logarithm of the volume ratios. All right, we can simplify this quite a bit if we just remember the trick that if we have something times a logarithm, that's equal to the logarithm of that original argument times the constant. We can bring, basically we can bring this right there. Okay, it's just a property of logarithms. So if we use that property, we get the log of t2 over t1 is going to be the log of t2 over t1 to the CV is going to be equal to the log of the volume ratio to the negative r. Okay, and now we can simplify this a little bit. Well, actually, it's pretty much simplified, but if we want to, we can express this just in terms of a temperature ratio. We can solve for the temperature ratio if we wish. So we could say that T2 over T1 is equal to the volume ratio. And let's go ahead and get rid of that negative sign by flipping over the V1 and the V2. So we've got just R now, and then we're going to take both sides to the 1 over CV. Okay, so now we have an expression that says that if we compress, if we go from a situation where the original volume gets put into a volume that's much smaller, this ratio is going to be greater than 1, and that tells us our temperature is going to go up, right? Our new temperature is going to be greater than our original temperature. So we can heat something up by adiabatically compressing it.